here, and that will be broken into two videos as it's kind of a big section here, as it takes on sun, stars, and galaxies. And the first thing we're going to look at here is the sun. Our chapter gives this section the heading "To Rule the Day," coming from the verse in Genesis, talking about when God made the lights in the sky on day 4. And it's the greater light to rule the day, the lesser night to rule, or the lesser light to rule the night. Referring to the sun and moon there. The sun is the most important star to us on the earth. It is the start of pretty much every process relates back to the sun in some way. The sun provides energy for plants to grow and to produce food, and then pretty much everything else lives off of those, off of plants. So the sun is really without the sun there would be no life on earth. That's one of the first requirements among several for life. The core of the sun, the center there, is around 27 million degrees Fahrenheit. The sun is broken up into several sections, just like we divided the Earth up into sections, the crust, mantle, core, and so on. The sun is divided up kind of in the same way. And the first one that we are looking at here is the photosphere, and that's the visible part of the sun. It's extremely bright, harmful to the eyes if observed directly. There are many ways to observe it indirectly, or even having protection. A welding mask will many welding masks will protect you from that. I've looked at a solar eclipse before through a welding mask, and I can still see. One of the things that we have observed as we've studied the surface of the sun are these granules, which look like little bubbles on the surface of the sun. They're over 600 miles across, and what they really are convection cells, where the hotter fluids rise to the top, cool off, sink back down, and we get convection cells. They're very similar to the convection cells we get here on Earth, except on a much grander scale, really. And then you also have these supergranules, which are a larger convection cell. Several convection cells are at about the same temperature, so they join together. Supergranules last for about 12 to 24 hours, maybe as much as 22,000 miles across. Mixed among the thousands of supergranules are dark patches called sunspots. These are caused by the sun's magnetic field. They appear darker than the rest of the sun because they are cooler than the granules that surround them. Scientists have discovered that sunspots follow a cycle of about 11 years. For a brief portion of the cycle, the face of the sun is practically empty of sunspots. Then the sunspots appear and begin to move diagonally across the face of the sun. Beyond being caused by the sun's magnetic field, we really have no idea why the pattern is the way it is. The movement of sunspots seem to indicate that the sun is actually spinning. And then we get to the next section of the sun, and that's the chromosphere. This lies outside the photosphere. It is the lowest layer of the sun's atmosphere, between 11,000 to 40,000 degrees Fahrenheit. If you look in the upper right-hand corner, we have a solar eclipse with the chromosphere visible around the moon there. During a solar eclipse, the chromosphere appears as a bright reddish-pink fringe around the blackened moon. Scientists can also view the chromosphere by using special filters that block out light from the photosphere. Allows them to see the chromosphere on the entire disk of the sun, not just around the edges. The moon is actually the right shape and the right distance from the Earth to the sun, that when it blocks out the sun, it does allow us to make certain observations and study it. Without the evidence of a solar eclipse, we wouldn't have had any reason to go looking for the chromosphere as a surface thing there, or part of the atmosphere there. So, just a little bit of good placement there to allow us to discover things. Flame-like columns of glass called spicules continually erupt from the chromosphere, last between 5 and 10 minutes, only about 600 miles across, about 6,000 miles high. The northern and southern edges of the sun, the spicules can grow to much greater height, around 24,000 miles. Because the spicules are shaped somewhat like blades of grass, the chromosphere has been described as a burning prairie. And the second picture here, just below the solar eclipse, shows some of these spicules there. Also of interest to us because they do affect us here on Earth. Solar flares. These are tremendous bursts of energy possibly caused by magnetic stress within the sun. They can disrupt radio communications and electrical power transmissions on Earth. I have never really seen much evidence of that in modern times. I think because our technology has taken solar flares into account. Every now and then, I've heard on the news, be patient with things because there's supposed to be a lot of solar flare activity. May disrupt cellular communications, usually the way I heard it. The only thing I remember vaguely is as I was growing up, before the advent of digital TV, before the advent of HD TV, every now and then the TV would be a little bit more staticky as it used the older style of transmitting pictures there. Solar prominences, streams of dense gas erupting off the chromosphere, returning in a loop. So they kind of look like solar flares, except they loop all the way back down to the sun's surface there. Some prominences appear to erupt out of sunspot areas of speeds of up to 2.4 million miles per hour. These prominences take the form of a loop joining two sunspots. Other prominences hover like thin clouds along the outer limits of the chromosphere. When the disk of the sun is viewed through special filters, dark lines called filaments appear to thread across its surface. These filaments are the same phenomenon as solar prominences, only viewed at a different angle. So these filters that we can put on telescopes and whatnot are giving us more insight as to what's going on there. We're seeing more connections. Exactly what they mean, we're still discovering and trying to figure out, because most of this has been within recent years that we've been able to develop this technology and see some of these other attributes there. The next layer here is the transition region. It's a very thin layer outside the chromosphere. The temperature in the transition regions varies quickly from 40,000 degrees to over almost 2 million degrees Fahrenheit. Because this region mostly releases ultraviolet radiation, which is blocked by the Earth's atmosphere, it can only be studied using space-based solar observatories. So basically, our atmosphere acts as a giant filter to keep these X-rays or ultraviolet rays, from reaching us. So space-based observatories such as Hubble and others have allowed us to study more about this transition region. And then we also see the corona, also visible during a solar eclipse, as pictured there. The outermost layer of the sun's atmosphere, corona, which means crown, a huge hot blanket of gas that extends hundreds of thousands of miles from the transition region, over 6 million degrees Fahrenheit. That's the hot part. The corona, like the chromosphere, is visible only during a total eclipse. Well, that is visible to the naked eye only during a total eclipse. It can be viewed through a telescope equipped with a coronagraph, a device that blocks light from the photosphere, making it observable. That's one of the things that the solar eclipse does for us, is it blocks that intense light coming from the photosphere, which drowns out all other areas of light emanation. So when there is a solar eclipse, we are able to see that chromosphere or the corona, depending on what we're looking at there. Another factor of the sun there are the solar wind. Coronal holes are the main source of the solar wind, a high-speed stream of charged particles ejected from the sun, traveling around 250 miles per second. Solar wind reaches the Earth in about 4.5 days. Most of it is blocked from reaching our surface by the magnetosphere. You may remember from earlier studies when we were looking at the magnetosphere that the solar wind actually deforms the magnetosphere of the Earth. Under no stress, the magnetosphere would form mostly a spherical shape. But because of the pressure from the solar wind, it makes it look more egg-shaped than round. So and for the most part, our magnetosphere blocks that. Now, every now and then, or rather the Aurora Borealis and the Aurora Australis, that's the solar winds getting funneled down into the north and south magnetic poles and interacting with our atmosphere, but the harmful radiation is not there, is not affecting us. So that's really it as far as the sun itself. Now, as we move out into space, we do need to get some... Oh, I forgot about the these pictures just some different false coloring pictures of the sun. I believe this particular picture was based off of temperature regions of the sun. You could see some corresponding areas there. Another one here just kind of showing the some of the parts of the sun's atmosphere. We have the photosphere way off on the right, chromosphere in the middle, transition region. Outside of that, we also have the spicules and corona labeled there. Now, getting into stellar measurements. There's just so much space out there in space that we need to have some better ways of telling distance. If we use miles, miles are simply too small. They're just not good enough. The distance from here, from the Earth to the Sun, is roughly 93 million miles. When we start getting further away from that, those numbers just start getting rather huge and unwieldy. So one of the first ones that we come up with, one of the most convenient ones, is the light year, the distance light travels in 1 year. Roughly, it travels at 186,000 miles per second. I believe that's about 300,000 meters per second, if I remember my conversions right. So in 1 year, it travels roughly 5.9 trillion miles. Inside the solar system, light years aren't quite as useful because our solar system is just shorter than that, so everything's less than 1 light year away. I mean, it takes only 8 minutes from light from the sun to reach the Earth here. So everything in the solar system would be measured in light hours or less. So within the solar system, light year may not be as useful as the astronomical unit, which is at 93 million miles I mentioned earlier. However, going outside our solar system, light years become very useful. The closest star to our sun is a little over 4 light years away. If we tried to measure that out in miles, that'd be somewhere around 24 trillion miles, give or take. Again, a little bit unwieldy. So, yeah, light years become very useful. Parallax is also a useful measurement, not so much as far as the distance a star is away, but really in its relationship to the Earth here. Parallax is the apparent change in the position of an object caused by the actual change in the position of the observer. Stars are far enough away that their movements really aren't seen and calculatable from Earth here. However, we're on Earth, and the Earth does move, and we can make calculations based off the movement of the Earth. This goes back to geometry, triangles, 90 degrees, and all similar triangles, and what we can do with that. If you look in your books on page 355, there's a very nice diagram showing how we utilize parallax. We take a measurement on one side of the sun 6 months later. We take a measurement for the same star on the other side of our sun, and we measure the distance between those measurements, calculating the Earth's distance from the sun, or using that calculation, and we can calculate the approximate distance it is. A stellar parallax is half the angle that the star appears to move on the celestial sphere when viewed from the opposite side of the Earth's orbit. Again, we can't really tell much about distance away from our sun here with this, but it does give us some clues to use. And that stellar parallax references the celestial sphere. Remember, as we're looking up from the Earth, it seems as if the Earth is surrounded by a two-dimensional plane with all these stars on it. Now, we know it's not two-dimensional, but that's the only way we can really observe it, because we just don't know for certain how far away some of these stars are, because the distance, or the perceived distance, is a function of the actual distance and the magnitude of the star. We just it's a complicated conversion or calculation, trying to do all that without any observable or first-person data there. The larger the stellar parallax, the closer the star is to the Earth, that's about what we can tell from the parallax. If there is very little stellar parallax, then it's going to be farther away, because the further away it is, the less change in relationship to the Earth there is. The closer it is, the larger the change in relationship to the Earth. So this gives rise to another unit of measurement, the parsec, which refers to a parallax second, the distance of an object with a stellar parallax of 1 second of arc. So it's a measurement of distance, not time. Thank you, George Lucas in Star Wars, when Han Solo boasts that he makes the Kessel Run in 12 parsecs. That line makes it sound like it's a measurement of time, that he shaved time off. Well, later on in some of the books, they had to come up with a way of making that statement work with what a parsec really is. They made it something along the lines of he got close enough to some of the black holes in that cluster that it actually did cut the distance that he traveled down to 12 parsecs. It's one of those interesting things where science fiction tried to catch up with science fact and tried to make a believable story as people become more educated about different areas of science, in this case, stellar science. So star magnitude, something about stars here, the different stars. Remember I said that figuring out the distance is a function of knowing what their magnitude is. Well, the only way we know what their magnitude is by observing it here on the Earth, and that really is the apparent magnitude, the brightness of a star as it appears to an observer on the Earth. Some stars are really, really bright and very far away, so the apparent magnitude is much higher than a star that is really close and really faint. So we can't just judge distance based on the apparent magnitude, which goes into number 2 there. Number 3, the absolute magnitude is the apparent magnitude a star would have to an observer located only 10 parsecs away. So much, much closer than we are to most of the suns, most of these other stars. Star categories are divided into temperature and color. A star's color depends primarily on its surface temperature, just like a fire depends a lot on its temperature. If you've ever used blowtorches, seen a regular fire, or even used a Bunsen burner in a chemistry class, they all have very different colors, and it's partially because of their temperature differences. A star's absolute magnitude depends on its surface temperature and its size. So that's something else that would affect its magnitude, which would affect how far away we understand it to be, is its size. So we make some educated guesses based off of temperature is fairly easy because we can look at the temperature. We have kind of a scale to go by that using our own sun. And size, again, we have some clues there as well. And these lead to the Hertzsprung-Russell diagram, or HR diagram. It's a two-dimensional diagram, which I have a picture of one on a different slide here, that compares stars by their temperature and by the amount of light they produce. And here we get the categories of giants and supergiants. Their brightness is due to their large size. There's also the main sequence. These are average stars on an HR diagram because their brightness depends primarily on their temperature. And we have some other distinguished categories here, and that's the red dwarf. Roughly about the same temperature as red supergiants, but produce much less light. Forgive my typos there. Our sun is a yellow star near the middle of the main sequence. And then we also have white dwarfs. These are groups of small dim stars outside the main sequence. Very hot, but dim because they are smaller than red dwarfs. And the next slide should be an HR diagram. You see this main sequence kind of running through the middle, curving off, going from blue to white to yellow to red. You look around the middle, just above the G in the OBAFGKM line there, just above the G, you see our sun there. You also see Alpha Centauri, which is a star very close to us, well, relatively close to us. Seems to be roughly about the same as our sun. So you could see several other stars are labeled on there. Beta Centauri is all the way up on the white-blue scale there. At the upper end, we also have Rigel as a white giant. And then we also have the white dwarfs and red dwarfs down there at the bottom. So go answer the science video question, and I will see you when we conclude this chapter.